everyone, welcome to the 7th video of Compiler Design series. In this video, we are going to study the Syntax Directed Translation Scheme or SDTS and solve a university question from past years. Before we start with SDTS, we must know what a programming construct is. A programming construct is a common building block of programming language. A programming construct can be arithmetic operations, Boolean operations, if-then-else statements, and many more we will study in upcoming videos. Whenever a compiler encounters a construct, it translates the construct into intermediate code, that is a 3-address code. It is done with the help of rules of translation that we call syntax directed translation. The given statement is p less than q and r less than s in parentheses or not t less than u and r less than q in parentheses. There are 4 steps to find 3-address code from a programming construct. The first step is to identify a programming construct. We can see relational operator between p less than q, r less than s, t less than u and r less than q. We see logical expressions and, or, and not. All programming constructs in the statement have been identified. The step 2 is to find associated SDTS. The SDTS or Syntax Directed Translation Scheme is a fixed and generic set of context-free grammar with semantic actions. We will use SDTS of programming constructs found in step 1. We found relational operators, logical and or not operators. For relational operators, this is the SDTS. The grammar is E derives ID relope ID, which will help to make the parse tree. We will look at all the semantic actions in step 4. For logical expression and, this is the SDTS, where grammar is E derives E1 and ME2, M derives epsilon. For logical expression or, this is the associated SDTS, where grammar is E derives E1 or ME2 and M derives epsilon. We will look at the semantic actions in step 4. For logical expression not, this is the SDTS, where the grammar is E derives not of E1. Step 3 is to draw syntactic structure, that is a parse tree. From step 2, we have a set of context-free grammars. To create the parse tree, we are going to break down the parsing construct with order of precedence of operator. The highest precedence is given to parentheses. The operation out of parentheses is OR. The NOT operator is a unary operator and it operates on contents of second parentheses. Therefore, we can start creating the parse tree from grammar of OR operator, which has the highest precedence in this case. The grammar of OR operator is E derives E1 or ME2 and M derives epsilon. We write each of the components here as node to the parse tree. We get root node E that derives E1 or M and E2, where E1 is P less than Q and R less than S. The node M leads to epsilon. And E2 is not of T less than U and R less than Q. Let's focus on E1, that is the first parenthesis. It contains 2 relational operators and 1 AND operator. Certainly, the highest precedence is given to the AND operator. We will draw the parse tree by its grammar, that is, E derives E1 and ME2, M derives epsilon. Here the root node for AND operation is E1. We can change the name of non-terminals in the grammar to remove any chances of ambiguity. So we rewrite E1 derives E3 and M1 E4 and M1 derives epsilon. Here E3 is P less than Q, M1 leads to epsilon and E4 is R less than S. The node E3 contains a relational operator less than. The grammar for relational operator is E derives ID relope ID. The relope is relational operator. Here root node of the operation is E3, so we can rewrite the grammar as E3 derives ID relope ID. Here ID is associated with the terminal P, relope with less than operator and second ID with Q. Let's go back up a node to node E1. Its child node E4 contains R less than S. It is the relational operator where the related grammar is E derives ID relope ID. We can rewrite it as E4 derives ID relope ID. Here ID is associated with the terminal R, relope with less than operator and second ID with S. Now we have made a complete parse tree for the first parenthesis. Now let's go back to the root node E. E1 has been taken care of. OR is the construct, we don't move it, and node M derives terminal epsilon. E2 contains second parenthesis, that is not of T less than U and are less than q. We can identify the logical operator not and also a relational operator less than. The operator with highest precedence is not. The grammar associated with it is e derives not of e1. We can rewrite it as e2 derives not of e5. e5 because the names e1, e2, e3, e4 are already taken. Here e5 contains the parentheses t less than u and r less than q. The and operator is of the more precedence as compared to the relational operator. The grammar for and operator is e derives e1 and m e2 and m derives epsilon. We can rewrite it as e5 derives e6 and m2 e7 and m2 derives epsilon. Here the node e6 is t is less than u and is the language construct and cannot be moved. M2 leads to epsilon and e7 is r less than q. We now focus on child nodes of e5 that are e6 and e7. e6 contains t less than u. It is a relational operator and its grammar will be e derives id relope id. We can rewrite it as e6 derives id relope id. Here id is associated with the terminal t, relope with less than operator and second id with u. Similarly for node e7, the construct r less than q is identified with the relational operator with grammar e derives id relope id. We can rewrite it as e7 derives id relope id. Here id is associated with the terminal r, relope with less than operator and second id with q. Now the parse tree is complete. Now moving on to step 4 to create workspace for 3-address code. A workspace uses the syntactic rules we saw in step 2. To create 3-address code, we look at the parse tree and perform topological sort. In simple words, we analyze the programming construct starting from leftmost child node on the lowest level of the parse tree. In this case, the leftmost and the lowest level of child node is E3 with relational operator construct and these are the syntactic rules associated with it. Here E3 is p less than q. If it is true, then we have to perform next quad. E3.true equals to next quad. The next quad operation works to provide an address to the condition it is equated to. In this case, E3.true. Let us assume the starting address to be 100, then E3.true equals to 100. The next condition is E3.false equals to next quad plus 1. The recent address is 100, that is next quad. So next quad plus 1 will be 101. Now we see gen code. If id relope id, then go to dash. Again gen code, go to dash. Gencode is the function that works to generate code on the addresses provided by nextquad. With gencode, we generate whichever code is inside the parentheses. That is, if id relope id, then go to dash and go to dash. These dashes are to be filled later. Here the first id is p, relope is less than symbol, and second id is q. The next node we go to is a programming construct AND, but this AND operation is between E3 and E4. We will leave it alone until we are done writing the semantics for E4. So we move on to the next node M1. The semantic actions associated with it are m1.quad equals to nextquad. Here nextquad generates a new consequent address. The next quad will be 102. The next node is E4 with relational operator construct. These are the syntactic actions associated with it. Here E4 is r less than s. If it is true, then we have to perform nextquad. Then E4.true equals the address generated by m1.quad, that is 102. The next condition is E4.false equals to nextquad plus 1. The recent address is 102, that is nextquad. Nextquad plus 1 will be 103. Now we see gencode. If id relope id, then go to dash and gencode go to dash. With gencode, we generate code that is inside the parentheses. That is, if id relope id, then go to dash and go to dash. Here the first id is r, relope is less than symbol, and second id is s, and the dashes will be filled later. Now that we have figured out all child nodes of E1, we can use the semantic actions associated with the AND operator. The curly braces contain semantic actions starting from backpatch e3.true, m.quad. e3.true is equals to 100 and m1.quad equals to 102. Therefore, we get backpatch 100 and 102. Backpatch is a function that has two parameters. It means we go to the address of first parameter and write the second parameter there in the place of empty space. So we go back to the line with address 100 and write 102 in the empty space we left earlier. Next condition is e1.true equals to e4.true. Here e4.true is 102. For next line, e3.false is 101 and e4.false is 103. The merge function will give control to the addresses mentioned as parameters after the condition of E1 fails. Now we have written 3 address code of nodes till E1. Next node in this line is node with programming construct OR. Firstly, we need to prepare node E2 for this operation. So we skip past it to node M. The semantic actions associated with it are m.quad equals to next quad. The address generated will be 104. The next node is E2. Its child nodes are programming construct NOT and E5. We cannot perform the next operation until node E5 is ready. So we move to the node E5. Its first child is node E6 with relational operator construct. These are the syntactic rules associated with it. Here E6 is t less than u. If it is true, then we have to perform next quad. Therefore E6.true equals to next quad and the latest next quad is 104. The next condition is E6.false equals to next quad plus 1. The recent address is 104, that is next quad. So next quad plus 1 will be 105. Now we see gencode. If id reloop id, then go to dash, gencode, go to dash. We generate the code with gencode, that is if id reloop id, then go to dash and go to dash. These dashes are to be filled later. Here the first id is t, reloop is less than symbol and second id is u. The next node we go to is a programming construct AND, but this AND operation is between E6 and E7. We leave it alone until we are done writing the semantics for E7. So we move on to the next node M2. The semantic actions associated with it are m2.quad equals to next quad. The next quad generates an address 106. The next node is E7 with relational operator construct. These are the syntactic actions associated with it. Here E7 is r less than q. If it is true, then we have to perform next quad. Then E7 equals the address generated by next quad, that is 106. Next condition is E7.false equals to next quad plus 1. The recent address is 106, that is next quad. Next quad plus 1 will be 107. Now we see gencode. If id reloop id, then go to dash, gencode, go to dash. With gencode, we generate code that is inside the parentheses. That is if id reloop id, then go to dash and go to dash. These dashes are to be filled later. Here first id is r, reloop is less than symbol and second id is q. Now that we have figured out all child nodes of E2, we can use a semantic action associated with AND operator. Starting from backpatch E6.true, m2.quad. E6.true is equal to 104 and m1.quad is equal to 106. Therefore, we get backpatch 104, 106. We are familiar with the backpatch function mentioned earlier. So we go back to the line with address 104 and write 106 in the empty space. The next condition is E5.true equals to E7.true. E7.true is 106. For next line, E6.false is 105 and E7.false is 107. The merge function will give control to the addresses mentioned as parameters after the condition of E5 fails. We have performed all the semantic actions on each of the child nodes of E5, so we can perform the NOT operation now. These are the associated actions. E5.false is merge of 105 and 107. So E2.true will be merge of 105 and 107. E5.true is 106. So E2.true will be 106. Now we go one level up. We were yet to perform the OR operation here. These are the semantic constructs. Even.false is merge of 101 and 103. M.quad is 104. We can write the backpatch merge of 101, 103 and 104. Go back to lines with addresses 101 and 103 and write 104 in the empty space. For next line, E2.false is 106. So E.false will be 106. Again, E.true is merge of E1.true and E2.true, where E1.true is 102, E2.true is merge of 105 and 107. This is the final 3 address code. Don't worry about the empty gotos. They indicate that there is no action to be taken if given condition stands or fails. In this video, we studied about OR, AND, NOT and relational operator constructs with an example of university question. Please like, subscribe and share. Thank you for watching.